Are we rolling, Bob? We are. Nature, accepted 31st of August 2023, published online 4th of October 2023, open access. Check for updates. Sharma, Sagal, Lachman, Kemps, Walker and Cronin. Assembly theory explains and quantifies selection and evolution. Scientists have grappled with reconciling biological evolution with the immutable laws of the universe defined by physics. These laws underpin life's origin, evolution, and the development of human culture and technology, yet they do not predict the emergence of these phenomena. Evolutionary theory explains why some things exist and others do not, through the lens of selection. To comprehend how diverse open-ended forms can emerge from physics without an inherent design blueprint, a new approach to understanding and quantifying selection is necessary. We present assembly theory, AT, as a framework that does not alter the laws of physics, but redefines the concept of an object on which these laws act. Object there is in inverted commas. Assembly theory conceptualizes objects not as point particles, but as entities defined by their possible formation histories. This allows objects to show evidence of selection within well-defined boundaries of individuals or selected units. We introduce a measure called assembly, A, capturing the degree of causation required to produce a given ensemble of objects. This approach enables us to incorporate novelty generation and selection into the physics of complex objects. It explains how these objects can be characterized through a forward dynamical process considering their assembly. By reimagining the concept of matter within assembly spaces, assembly theory provides a powerful interface between physics and biology. It discloses a new aspect of physics emerging at the chemical scale, whereby history and causal contingency influence what exists. In evolutionary theory, natural selection describes why some things exist and others do not. Darwin's theory of evolution and its modern synthesis point out how selection among variants in the past generates current functionality, as well as a forward-looking process. Neither addresses the space in which new phenotypic variants are generated. Physics can, in theory, take us from past initial conditions to current and future states. However, because physics has no functional view of the universe, it cannot distinguish novel functional features from random fluctuations, which means that talking about true novelty is impossible in physical reductionism. Thus, the open-ended generation of novelty does not fit cleanly into the paradigmatic frameworks of other biology or physics, and so must resort ultimately to randomness. There have been several efforts to explore the gap between physics and evolution. This is because a growing state space over time requires the exploration of a large combinatorial set of possibilities, such as in the theory of the adjacent possible. However, the search generates an unsustainable expansion in the number of configurations possible in a finite universe in finite time, and does not include selection. In addition, this approach has limited predictive power with respect to why only some evolutionary innovations happen and not others. Other efforts have studied the evolution of rules acting on other rules. However, these models are abstract, so it is difficult to see how they can describe and predict the evolution of physical objects. Here we introduce assembly theory, which addresses these challenges by describing how novelty generation and selection can operate in forward evolving processes. The framework of AT allows us to predict features of new discoveries during selection and to quantify how much selection was necessary to produce observed objects, without having to pre-specify individuals or units of selection. In assembly theory, objects are not considered as point particles, as in most physics, but are defined by the histories of their formation as an intrinsic property, mapped as an assembly space. The assembly space is defined as the pathway by which a given object can be built from elementary building blocks using only recursive operations. For the shortest path, the assembly space captures the minimal memory in terms of the minimal number of operations necessary to construct an observed object based on objects that could have existed in its past. One feature of biological assemblies of objects is multiple realizability, wherein biological evolution can produce functionally equivalent classes of objects with modular use of units in many different contexts. For each unit, the minimal assembly is unique and independent of its formation, and therefore accounts for multiple realizability in how it could be constructed. We introduced the foundations of assembly theory and its implementation to quantify the degree of selection and evolution found in a collection of objects. Assembly is a function of two objects. I beg your pardon. Assembly is a function of two quantities: the number of copies of the observed objects and the object's assembly indices. An assembly index is the number of steps on a minimal path producing the object. Assembly captures the amount of memory necessary to produce a selected configuration of historically contingent objects in a manner similar to how entropy quantifies the information, or lack thereof, necessary to specify the configuration of an ensemble of point particles. But assembly differs from entropy because of its explicit dependence on the contingency in construction paths intrinsic to complex objects. We demonstrate how assembly theory leads to a unified language for describing selection and the generation of novelty, and thereby produce a framework to unify descriptions of selection across physics and biology. Assembly theory. The concept of an object in assembly theory is simple and rigorously defined. An object is finite, is distinguishable, persists over time, and is breakable, such that the set of constraints to construct it from elementary building blocks is quantifiable. This definition, in some sense, opposite to standard physics, this definition is, in some sense, opposite to standard physics, which treats objects of interest as fundamental and unbreakable. For example, the concept of atoms as indivisible, which now applies to elementary particles. In assembly theory, we recognize that the smallest unit of matter is typically defined by the limits of observational measurements and may not itself be fundamental. A more universal concept is to treat objects as anything that can be broken and built. This allows us to naturally account for the emergent objects produced by evolution and selection as fundamental to the theory. The concept of copy number is of foundational importance in defining a theory that accounts for selection. The more complex a given object, the less likely an identical copy can exist without selection of some information-driven mechanism that generates that object. I'd like to come back to that sentence. Information, yes, that's true, okay, fine. An object that exists in multiple copies allows the signatures describing the set of constraints that build it to be measured experimentally. For example, mass spectrometry can be used to measure assembly for molecules because it can measure how molecules are built by making bonds. Assembly index and copy number. To construct an assembly space for an object, one starts from elementary building blocks comprising that object and recursively joins these to form new structures whereby, at each recursive step, the objects formed are added back to the assembly pool and are available for subsequent steps. See some supplementary information in sections 1 and 2. Assembly theory captures symmetry breaking arising along construction paths due to recursive use of past objects that can be combined in different ways to make new things. For any given object I, we can define its assembly space as all recursively assembled pathways that produce it. For each object, the most important feature is the assembly index, AI, which corresponds to the shortest number of steps required to generate the object from basic building blocks. This can be quantified as the length of the shortest assembly pathway that can generate the object. See figure 1. In chemical systems, molecular assembly theory treats bonds as the elementary operations from which molecules are constructed. The shortest path to build a given molecule can be found by breaking its bonds and then ordering its motifs in order of size, starting from atoms and moving to larger motifs by adding bonds in sequence. Given a motif generated on the path, the motif remains available for reuse. The recursivity allows identifying the shortest construction path with parts already built on that path, allowing us to quantify the minimum number of constraints or memory size to construct the molecule. The assembly index can be estimated from any complex discrete object with well-defined building blocks, which can be broken apart, as shown in figure 1. At every step, the size of the object increases by at least 1. The number of total possible steps, although potentially large, is always finite for any finite object, and thus the assembly index is computable in finite time. For molecules, the assembly index can be determined experimentally. A hallmark feature of life is how complex objects are generated by evolution, of which many are functional. For example, a DNA molecule holds genetic information reliably and can be copied easily. By contrast, a random string of letters requires much more information to describe it, but is not normally seen as very complex or useful. Thus far, science has not been able to find a measure that quantifies the complexity of functionality to distinguish these two cases. Here, we overcome this inherent problem by pointing out another feature of the evolutionary process. The complex and functional objects it generates take many steps to make, and selection allows many identical copies of these objects. Therefore, an evolutionary process can be identified by the production of many identical or near identical multi-step objects. The assembly index on its own cannot detect selection, but copy number combined with the assembly index can. This approach defines a new way to measure complexity in terms of the hierarchy of causation stemming from selection at different levels. Because we do not typically know the full assembly trajectory of an object, we instead adopt a conservative alternative. Assembly theory finds the minimal number of steps to produce the object. We assume that every sub-object, once available, can be used as often as needed to generate the entire object. I put the word entire in. A different approach would be to use Kolmogorov complexity applied to a given molecule, but this requires starting with a graphical representation and a program to compute the graph of that molecule. The Kolmogorov complexity of a string is the shortest possible program that will output that string for a programming language capable of universal computation. This measure cannot be easily computed because checking whether any single program will output the string is uncomputable, as it involves at least deciding whether the program stops. Running this program reflects nothing of the underlying process of how the molecule was constructed. Only late in the evolutionary process will molecules be produced by anything starting to resemble Turing machines, loops, stacks, tapes, and so on. Thus, using universal computation to assess molecules adds unrealistic dynamics, making the answer uncomputable. The assembly measure that we have presented here both uses realistic dynamics for molecules using bonds as building blocks and is computable for any molecule. The main work for detecting evolution and memory is done here by combining the assembly index and the copy number of the objects. The aim of assembly theory is to develop a new understanding of the evolution of complex matter that naturally accounts for selection and history in terms of what operations are physically possible in constructing an object. We will discuss assembly theory as applied to chemical systems as the main application in this manuscript, because their assembly index has been experimentally measured. For molecules, assembly index has a clear physical interpretation and has been validated as quantifying evidence of selection in its application to the detection of molecular signatures of life. However, we anticipate the theory to be sufficiently general to apply to a wide variety of other systems, including polymers, cell morphology, graphs, images, computer programs, human languages, and memes, as well as many others. The challenge in each case will be to construct an assembly space that has a clear physical meaning in terms of what operations can be caused to occur to make the object. See again figure 1. In assembly theory, there are two important features of the context of the object is found in. First, there must be objects in its environment that can constrain the steps to assemble the object, and second, these objects themselves have been selected because they must be retained over subsequent steps to physically instantiate the memory needed to build the target object. Among the most relatable examples are enzyme catalysts in biochemistry, which permit the formation of very unlikely molecules in large numbers because the enzymes themselves are also selected to exist with many copies. We make no distinction between the traditional notion of biological individual and objects that are selected in the environment to quantify the selection necessary to produce a given configuration. Thus, our approach naturally accounts for well-known phenomena such as niche construction, whereby organisms and environment are co-constructed and co-selected. Copy number is important because a single example of a highly complex molecule with very high assembly index could potentially be generated in a series of random events that become increasingly less likely with increasing assembly index. If we consider a forward-building assembly process, see supplementary information sections 1 and 2 for details, without a specific target in mind, the number of possible objects that could be built at each recursive step grows super exponentially in the absence of any constraints. The likelihood of finding and measuring more than one copy of an object therefore decreases super exponentially with increasing assembly index in the absence of selection for a specified target. I would have said for a specific target. Objects with high assembly index found in abundance provide evidence of selection because the combinatorially growing space of possible objects at each recursive assembly step finding more than one identical copy indicates the presence of a non-random process generating the object. The assembly equation. We define assembly as the total number of selection. We define assembly as the total amount of selection necessary to produce an ensemble of observed objects, quantified using the equation assembly index is equal to the sum from I to 1 to n of e to the AI multiplied by the number of the index minus 1 divided by the total number of objects. A is the assembly of the ensemble. AI is the assembly index of the object I. Ni is its copy number. N is the total number of unique objects. E is Euler's number. And Nt is the total number of objects in the ensemble. Normalizing by the number of objects in the ensemble allows assembly to be compared between two ensembles with different numbers of objects. Assembly quantifies two competing effects: the difficulty of discovering new objects, but once discovered, some objects become easier to make. This is indicative of how selection was required to discover and make them. The exponential growth of assembly with depth in assembly space, as quantified by assembly index, is derived by considering a linearly expanding assembly pool that has objects that combine at step A maps to A plus 1, whereby an object at the assembly index A combines with another object from the assembly pool. Discovering new objects at increasing depth in an assembly space gets increasingly harder with depth because the space of possibilities expands exponentially. Once the pathway for a new object has been discovered, the production of an object, copy number greater than 1, gets easier as the copy number increases, because a high copy number implies that an object can be produced readily in a given context. Thus, the hardest innovation is making an object for the first time, which is equivalent to its discovery, followed by making the first copy of that object. But once an object exists in very high abundance, it must already be relatively easy to make. Hence, assembly A scales linearly with copy number for more than one object for a fixed cost per object once a process has been discovered. See section 3 for additional details. Increasing assembly A results from increasing copy numbers N and increasing assembly indices A. If high values of assembly can be shown to capture cases in which selection has occurred, it implies that finding high assembly index objects in high abundance is a signature of selection. In assembly theory, the information required at each step to construct the object is stored within the object. Stored is in inverted commas. Figure 2. Each time two objects are combined from an assembly pool, the specificity of the combination process constitutes selection. As we will show, randomly combining objects within the assembly pool at each step does not constitute selection, because no combinations exist in memory to be used again for building the same object. If instead certain combinations are preferentially used, it implies that a mechanism exists that selects the specific operations and, by extension, specific target objects to be generated. Later we will quantify the degree of selectivity by the parameter alpha in the growth dynamics, which allows parameterizing selection in an empirically observable manner by parameterizing reuses of specific sets of observations. Assembly, as given in equation 1, is determined for identified finite and distinguishable objects with copy numbers greater than 1 and their distinct assembly spaces. However, in real samples, there are almost always, several different coexisting objects, which will include a common history for their formation. Transistors, for example, are used across several different technologies, suggesting a common subspace in the assembly spaces of many modern technologies that include transistor-like objects. This common subspace, constituting the overlap in the assembly paths of distinct structures, is called a co-assembly space. By contrast, a joint assembly space of several objects is the combined assembly space required to generate those objects. As a potential extension of the assembly equation to account for the joint assembly of objects, we expand the formulation of the assembly equation that includes the quantification of shared pathways to construct objects to determine the assembly A of an ensemble with different objects that share common history. See supplementary information, section 3. Pause for reflection. Well, I get it. It makes sense. I was distinctly surprised that Lex didn't sort of leap on this and say, this is how I work in my large language models, artificial intelligence, like how I parse through a document or through a photograph or even through a video to say what is the persistence of an object or something of that sort, a colour, theme, a fractal pattern, a deconstructed fractal pattern of something. What does figure 1 and 2 look like? I haven't really properly looked at them yet. 1 is clearly just breaking molecules up and looking at assembly pathways, sure. What do you think, Foxy? Pictorial representation of the assembly space representing the formation of combinatorial object space from building blocks and physical constraints. Observe copy number distributions of objects at different assembly indices as an outcome of selection or no selection. C. Representation of physical pathways to construct objects with undirected and directed or selected pathways leading to the low and high copy numbers of the observed object.
Well, that's a start.